Welcome to 4.4, the Fundamental Theorem of Calculus, Day 2. So we're going to get into the mean value theorem for integrals. We're going to talk about that. We're going to find the average value, and then we'll do a bunch of examples. So let's get into it. The mean value theorem for integrals says, if f is continuous on the closed interval ab, then there exists a c in the closed interval such that the integral from a to b of f of x dx is equal to f of c times b minus a. So it's almost like a rectangle. So we can think of this as our area, all right, and that's equal to our height of our rectangle times the base. And essentially what this is saying is, all right, well, what if we kind of flattened this curve out to look like this rectangle? So instead of this F piece being all curvy, it's essentially saying I can flatten it out to create this rectangle that I'm finding the area of. So it's like the mean value rectangle. So it's this formula right here, F of C times B minus A is equal to the integral, is equal to the area under that curve. Okay, so that's the mean value of that rectangle, saying when the rectangle is the same area as the area under the curve. Okay, so then keep going. The definition of the average value of a function of an interval, or on an interval, says if f is integrable on the closed interval ab, then the average value of f on the interval is this guy right here. Well, you can kind of see how that works, right? Before we talked about how we had f of c times b minus a is equal to the integral, right, of f of x dx. Now it's essentially saying, well, that f of c is equal to that 1 over b minus a times our integral. Okay, so that's our average value. That's what we're thinking about right there. So I want to know the average value. So I'm going to take that area underneath the curve, and I'm essentially going to divide it by my interval, 1 over my b minus a. All right, so now let's just get into some examples here. The first example says find the value or values of c that's guaranteed by the mean value theorem for integrals for the function f of x equals x minus 2 root x on our interval 0 to 2. So remember, mean value theorem is this guy right here. So as we go through and we do our setup, all right, I'm going to set up our integral and using that mean value theorem. So we have the integral from our interval 0 to 2 of f of x is equal to f of c times b minus a. Well, b is 2 and a is 0. So now we're just going to integrate and clean things up. So when we integrate x, we get 1/2 x squared. If we think about the square root of x as x to the 1/2, all right, we still have minus 2. That x is going to add 1, so we're going to get 3/2. So we have to kind of take the reciprocal, right, because that's our denominator. And so we get 2/3 x to the 3/2. We're going to evaluate this integral from 0 to 2 and then just cleaning up that right side. So I'm not changing much on the right side. Now we're just going to evaluate the left. When I plug 2 in, we get this, 2 minus 4/3 times 2 root 2. When we plug 0, all this goes away. We're left with minus 0. So cleaning up that left side, all right, and now solving for f of c. So when we do that, we end up getting f of c to be this right here, 1 minus 4/3 times the square root of 2. So now what we need to do is actually find what that c value is. Okay, so now f of c, what we just found, right, f of that c value equals that 1 minus 4/3 root 2. So now I'm just plugging c into our function f of x. So we have c minus 2 root c is equal to 1 minus 4/3 root 2. Well, in order to solve for c, we need to complete the square. So it looks just a little different because it's a c to the first, but a c to the 1/2. So if we complete the square like we've done in the past, right, I'm just going to rewrite this square root of c to be c to the 1/2. Take our middle term divided by 2 and square it is where we get 1. Whatever I do to one side, I've got to do to the other. So now we clean up the right side. When we factor this left side, it factors as a perfect square. Square root of c minus 1 squared. And now we just finish it off, right? We take the square root of both sides, and when we do that, we can't forget that plus or minus. And as we continue, you'll see our final answer. The last thing I'll have to do is just add 1 to the other side. And then, so that's going to get us to the square root of c. Let's change that. We'll have the square root of c is equal to 1 plus or minus the square root of 2 minus 4/3 root 2. And then to get c by itself, we just have to square the whole thing. So there's our final answer of what c is. It's very ugly, but we get there. This next example wants us to find the average value of f of x over our interval and all values of x for which the function equals its average value. So I'm just going to zoom in and we'll go through things. So remember, average value is equal to 1 over b minus a times the integral of a to b of f of x. Now remember, this average value, this is like saying our f of c here is equal to this. So we have f of c equals, we're just plugging in, okay, here's our a and our b, or our a and our b, and our integral. So now we're going to integrate it. So 1 over 3 is from this portion up front. Integrating 4x cubed minus 3x squared, we get x to the 4th minus x cubed. We're going to evaluate that from -1 to 2. So when we plug in 2, we get 16 minus 8, minus when we plug in -1, we get 1 plus 1. So what we end up with is f of c equals 2. But it wants us to find that c value, right? So now we need to find the c value when f of c equals the average value, okay? All right. So now f of c is equal to 2, so we're just plugging that into our original function, f of x, and we solve. Now we get to this cubic function. This is where we can go to our calculator, throw it into y equals, calculate the 0, and on the interval, we're only going to get one of these zeros. Okay, so be careful. Remember to note the interval that we need to be on. And when you do everything correctly, you'll get this to be the 0. So this is our c value that satisfies this problem. This next example says the graph shows the velocity in feet per second of a decelerating car after the driver applies the brakes. Use the graph to estimate how far the car travels before it comes to a stop. All right, so quick reminder, distance traveled is equal to the integral from a to b of the velocity. So if we know that this is our velocity, then the distance traveled is simply the integral of this. Now, when we're talking about integrals, we're simply finding the area under the curve, okay? So that's what we're trying to do. And it just says to estimate. So there's kind of two ways we can go about it. So if you take a look at it, well, one thing I notice is this kind of looks like a right triangle, right? So if I were to connect here, we could say, oh, well, that's almost like saying the area is equal to the area of this triangle. So the area of the triangle is 1/2, our base is 5, and our height is 80. And when we do this, we get it to be 200 feet. So I could say, oh, well, the area is roughly 200 feet, okay? So that's how far the car traveled, roughly 200 feet. The other way you could look at it is if we count the squares. Okay, so if I count the squares underneath here, so I'm going to count kind of these full squares. So if we kind of go through and count all of these, and then you can kind of look and see, all right, Here, this guy right here is a little bit of one, but if I add that to this guy, that gets another square, and you can kind of go from there and adding them all up. So if we do that, I kind of counted, so I could say, or the area is about roughly, if you do this, we get about 29 squares. All right. And each square is about, 5 feet per square. Okay, if we're kind of looking at all these. And so this comes out to be about 145 feet. So both of these are estimates, okay? The triangle was obviously an overestimate because our hypotenuse went outside of it. But it's certainly different ways you can go about estimating the total distance traveled. This next example, we're going to walk through using this graph, okay? And this is a graph of f of t, okay? F of t. So one thing we're going to do is we're going to let g of x equal the integral from 0 to x of f of t dt. All right, so we're going to use that to answer the following questions. Okay, I'm going to walk through A with you just for the first 3, and then I want you to finish the evaluating the rest. So in part A, it wants us to estimate g of -4, g of -2, g of 0, g of 2, g of 4, and g of 5. So remember, g of -4 is like saying the integral from 0 to -4 of f of t. Okay, so we're looking at the area. Now remember, since it goes from 0 to -4, this is the same as saying the opposite of the integral from -4 to 0. So we're looking at this piece here. So we want to find the area under the curve. So we're going to add up this piece plus this piece because that's going to get us to 0. All right? So if we go through, we're really looking at the opposite of the integral from -4 to 0. So we have this triangle, which is where we get 1/2 times 1 times 2, 1/2 base times height. And then we have our trapezoid, but we're going to subtract that because it's negative area here. So 1/2, the height is 2, and the sum of our bases is 3 plus 1, so that's where we get 4. When we clean this all up, we get g of -4 to be 3. The next thing we're going to try to do is find g of -2. So again, this is the integral from 0 to -2 of f of t. And this is like saying the opposite of the integral from -2 to 0. So when we're looking at our graph, we're really just looking at this portion here that I'm highlighting in green. Okay? So now we're just finding the area of that trapezoid. All right, so we have 1/2 our base, or sorry, 1/2 our height. Our height is negative. All right, and the sum of our two bases is 2 plus 1, and that's where we get 3. So when we clean this up, we get g of -2 to also be 3. Then we have to find g of 0. So this is like saying the integral from 0 to 0. So remember when we first started talking about integrals, we know right away that the integral from 0 to 0 is simply 0. All right, so what I want you to do is I want you to find the rest. I want you to find what g of 2 is, g of 4, and g of 5. Find that, come back, and let's check. Okay, so hopefully you got what I got. G of 2 is 3. So we're looking at the area from 0 to 2. All right, so you're looking at this trapezoid here. And then we want g of 4. So g of 4 is now looking at the area of this entire trapezoid plus half of this semicircle, but remember that's going to be negative, so that's where we got 1/2 times 2, that's the height of our trapezoid and the sum of the bases, and then we're subtracting the quarter of a circle. So we get 4 minus pi over 4, which is around 3.2. Then the very last thing we're trying to find is g of 5, which is the area under the curve from 0 to 5. So this whole trapezoid again, plus the entire, or subtracting the entire semicircle. So we already found the area of this trapezoid to be 4, and now we're just subtracting that semicircle, and that comes out to be 2.4. The next thing it asks is for us to find the largest open interval on which G is increasing, okay? So when G is increasing, so what this really means is I want to know the most positive area, okay? So if we're taking a look at where there's some positive areas, we have the interval from -4 to -3, and then we also have from 0 to 3. So if we're just looking at it, which area is the biggest, we could go ahead and say on the interval from 0 to 3 is where it is increasing the most, the largest open interval for which it's increasing, okay? Then for decreasing, we're looking on intervals where we have negative areas, okay? So we have from -3 to 0, and we also have from 3 to 5, that interval. So which one is the most negative? Well, hopefully you can look at it and see, well, the interval from -3 to 0 is the largest open interval where G is decreasing. Next, we want to find the extrema of G. So we have to make note of this. We're given that G of x is equal to the integral from 0 to x of f of t dt. So what does that tell us? It tells us that f is the first derivative of G, right? Because typically when you take the integral, this is the derivative portion, okay? So we can say f is equal to G prime. So if we're looking at the graph, remember the graph is of f, okay? So if we're looking at finding our critical numbers, I want to know when f changes from positive to negative or negative to positive, or when f equals 0. So f equals 0 at x equals, or t equals -3, 0, and 3. So those are going to be our critical numbers. So that's why I wrote those down here, okay? And now we're just going to use the graph to go ahead and talk about the sign of G. So if we take a look to the left of -3, G prime is positive. Between -3 and 0, looking again at the graph, G prime is negative. 0 to 3, we're back to positive. And 3 on, we're back to negative. So what does that mean about G? What's happening to G? Well, we're increasing, then decreasing, increasing, and decreasing again. So we can go ahead and say at t equals -3, we have a max, we have a min at 0, and we're back to another max here. So that's going to help us when it's time to graph. Okay, so we're going to keep that in mind. I'm going to go ahead and kind of draw in my notes here. Okay, at x equals -3, we are going to have a maximum. At x equals 0, we have a minimum. And then at x equals 3, we're back to a maximum. Now, from part A, we know all of these points. So we can go ahead and plot those, all right, on our graph. So we have when x is -4, we get y to be 3. When x is -2, we're also at 3, and we're at 0, 0. Then we're at the point 2, 3. And then we're at the point 4, about 3.2, and then 5 and 2.4. So we're about there. And again, we know that we have a maximum here, a minimum here, and another maximum there. So we can go ahead and draw our graph accordingly. So I know I'm going to go up, and then we're going to come back down. We've got a minimum at 0. That's where we go up, and then we finish the graph. All right? So if you have any questions on this, let me know next time we see each other.